Okay, so quantum numbers are basically the numbers which are needed to specify electron present in a particular orbital. So you can say that in an atom there are various shells or various main energy levels, and in these shells, in these main energy levels, there are various subshells. So we can say that in an atom there are shells, then in those shells there are subshells. Okay, then in those subshells there are orbitals, and in orbitals there are electrons. To specify an electron present in an orbital, we need the quantum numbers. So the first quantum number which we are going to talk about is a principal quantum number, which tells us about the main shell, okay, or main energy level in which the electron is present. Okay, so you can see that this is an atom. Half picture of an atom is shown, and here is an nucleus, and these are all the main energy levels around the nucleus. And in these levels there are subshells, and in those subshells there are orbitals, and in those orbitals there are electrons. So we need to specify the electron by specifying the main energy level. So for this, the principal quantum number comes in, and it is denoted by a symbol, by a letter n. And if n is equal to 1, that means we are talking about the first energy level. If n is equal to 2, we are talking about the second energy level. And in this way it goes on. And also size and energy of the orbital are also determined by knowing about the principal quantum number. So if n is equal to 1, if we are talking of an electron present in an orbital which is present in first energy level, then the orbital will be small, and since it is closest to the nucleus, the orbital will be small in size, and its energy will also be less when compared to the orbital which is present in the second energy level. See, it becomes farther from the nucleus, and its size will also increase because it is farther from the nucleus, and its energy will also increase. So as we move away from the nucleus, the size of the orbitals present in these energy levels becomes larger, and also the energy, as the distance from the nucleus increases, the energy also increases of the electrons present in those orbitals. So you can see it better in this slide, as you can see there is 1s orbital, 2s and 3s orbitals. As s orbitals are spherically symmetrical orbitals, and 1s orbital, since it is 1 here denotes the principal quantum number, 2 here denotes the second energy level, 3 here denotes the third energy level. So in the first energy level, which is closest to the nucleus, the orbital size is smaller, and as we move farther from the nucleus, or as the n increases from 1 to 2 to 3, the size of the orbital also increases. Okay, so this is the animated picture, and this is the real picture of the electron cloud present in the 1s, 2s and 3s orbitals. So electrons are basically presented as dots. The density of the dots actually is the most probable place, determines the most probable place where the electron is most likely to be found. So electrons are basically moving, there are only 2 electrons in every orbital, but the dot density represents that electron is moving in this region more than is moving in this region where the dot density decreases. So electron movement is basically denoted by the movement of the, just like a moth, when you switch on the light, the light moths, they move around this light. In the same way, the electrons have a very random movement around the nucleus. So in 3s orbital also you can see the same dot density is here more. That means the probability of finding the electron in this very portion is more than in this portion. And also you can see the white portions here and here. So these white portions do not have or you negligible amount of dots, or these portions are actually called as nodes, where the probability of finding the electron is 0. So we denote these portions as nodes. These are nodes. Okay, so in 3s orbital you can find that there are two nodes. See, one node is here and the second node is here. In the 2s you can find one node only near the at this place. So the number of nodes can be calculated. Number of nodes in any orbital can be calculated by knowing the principal quantum number of that orbital. Say for example you have to calculate the number of nodes in 3s, so you know the principal quantum number is 3 here, n is equal to 3, and the number of nodes are always equal to n minus 1. That means in 3s orbital the number of nodes will be 3 minus 1, that is 2. In 3s orbital there will be 2 nodes. In 2s orbital in the same way n minus 1 number of nodes will be there, where n is equal to 2. So 2 minus 1, that is 1. So you can very well see here that there is only one node in 2s. In 3s there are two nodes, here one and here another one. So in this way it goes. Now we will talk about the azimuthal quantum number. So you come to know that principal quantum number tells you about the electron main energy level. Okay, if you say that n is equal to 1, that means you are talking about the electron present in the first energy level, nothing else. A principal quantum number defines the energy level, main energy level. Now we'll come to the azimuthal quantum number. Okay, so azimuthal quantum number talks about the subshells. The subshells which I have told you earlier, that they are in these main energy levels, there are, or in these subshells there are present various in these shells there are present various subshells. So azimuthal quantum number define those shells, that in which shell actually the electron is present. In those many shells which are present in this orbit, in these shells where the electron is basically present, this is given by the azimuthal quantum number, which is denoted by the letter L. So these are the subshells. This is S subshell. This is P subshell, which consists of 3 orbitals. This is D subshell, which consists of 5 orbitals. This is F subshell, which consists of 7 orbitals. So these subshells are present in these main energy levels. And so azimuthal quantum number defines the subshell of the electron. Okay, so it basically defines the shape of the orbital. So if the subshell is S, that means the spherical shape of the orbital is present. If the subshell is P, that means the dumbbell shaped or orbital is there in which the electron is present. So in this way azimuthal quantum number tells us about the shape of the orbital in which the electron is present, and its value ranges from 0 to n minus 1. So if you know about n, if you are being given the main energy level number, if you are given the principal quantum number, so you will come to know the azimuthal quantum numbers or number of shells present in that very orbital, in that very shell. For example, let us see here that these are main energy levels. They are being numbered by principal quantum number. N is equal to 1 for this, n is equal to 2 for this n is equal to 3, and for this n is equal to 4. So azimuthal quantum number ranges from 0 to n minus 1. So for, let's say, for this first energy level, L will be equal to 0 to n minus 1. That is, L will be equal to 0 to 1 minus 1. N is 1 here. So 0 to, you can say that from 0 to 0, that is L value comes out to be 0. Okay, no other value of L is there in the first energy level. So when L value comes out to be 0, then this 0, as if azimuthal quantum number is 0, that means there is only S subshell. Okay, so L value 0 denotes S subshell, and you can see here that this is uh, um, uh, 1 second, this is here, see 1s subshell is present only in the first energy level. There is one subshell that is named as 1s. Okay, in the same way, when we come to n is equal to 2, so there are two subshells, we can calculate it. When n is equal to 2, L will be equal to 0, 2 and minus 1. That means 0, 2, n is here 2, so 2 minus 1. That means 0, 2, 1. This comes out to be, L value will be equal to 0 and 1. L value is here in this second energy value. L has two values. Azimuthal quantum number has two values, that is 0 and 1. 0 stands for S subshell and 1 stands for P subshell. So you can see in the second energy level there are two subshells. One is S subshell and the other one is P subshell. In the same way it goes on for n is equal to 3 and n is equal to 4. Okay, so in this you can see n is equal to 3. So L value here will be equal to 0, 2, n minus 1. That is L will be equal to 0, 2, 3 minus 1. Here the number of principal quantum number is 3. So it will be equal to 3 minus 1. That means 0, 2, 2. That means L's value will come out to be 0, 1 and 2. For 0, the subshell denoted is S. For 1, the subshell denoted is P. And for 2, the subshell denoted is D. In the same way, it goes on for other subshells as well. So here you can see that for n is equal to 4, there are 4 subshells. So which are 4s. Here the L value will come out to be, oh sorry, let me take the eraser and rub it off. Here the L value will be 0, 2, 4 minus 1. That means 0, 2, 3. That means 0, L value will be equal to 0, 1, 2 and 3. The 4 values of L will come. It means that there are 4 subshells present in the fourth energy level. Okay, in the fourth energy level there are 4 subshells, 0, 1, 2 and 3. 0 stands for S, 1 stands for P, 2 stands for D and the 3 stands for F. Okay, so there are 4 subshells in the fourth energy level. So you can see that the number of subshells depend upon the principal quantum number. If the principal quantum number is 1, the subshell is also 1. If the principal quantum number is 2, the subshell is also 2. In the same way, if the principal quantum number is 4, the subshells are also 4. Now when you have known the principal quantum number and the azimuthal quantum number of the electron, and you have specified the main energy level by knowing the principal quantum number, and the subshell present in that very energy level by knowing the azimuthal quantum number. So now you need to know what is the orientation of that very orbital in which the electron is present. So this is given by the magnetic quantum number. I can explain you through taking an example that let us suppose that you are given that person is talking about an electron which is present in the n is equal to 2 energy level. That means the second energy level. You are given with the principal quantum number which is 2. This shows that the electron is present in the second energy level, in this very energy level. And then you are given an azimuthal quantum number which is 1. So this shows that the electron is present in P subshell. The main subshell is the second shell, and in that very second shell there are subshells which are specified by knowing the azimuthal quantum number. So azimuthal quantum number is given 1. That means the subshell is P. For L is equal to 1, the subshell is P. So basically the person is talking about the two-piece subshell. Okay, now